The next company we have on board is Tightbeam Laser Communication. Tightbeam Photonics builds low-cost optical ground stations for space-to-ground laser communications. They're removing a major bottleneck in satellite data transmission. Presenting Tightbeam Laser Communications. Over to you.
Hello, everyone. I'm Mark Barnett from Tightbeam Photonics. We're building optical ground stations for the speed and security of fiber communication, but anywhere. So there is a huge demand for high bandwidth communication in our world. Particularly with regard to space to ground communication, we have low Earth orbit constellations, we have Earth observation satellites, data centers in space, and now quantum communication, which will be using space infrastructure. The problem with this is all it uses RF, radio frequency, and RF speed is quite limited. It has to operate in licensed spectrum. Spectrum is really is getting jammed up right now. It's a finite resource. There's only so much spectrum that can be licensed, and it's scarce with this growing need for data. Costs are going non-linear. In September, SpaceX spent $23 billion to buy EchoStar Communications, and that was principally for their 50 megahertz of spectrum. There's an alternative, free space optical communications or laser communications. It doesn't suffer from most of these problems. It has communication speeds on the order of terabits per second. It does not use RF spectrum. It operates completely independently of spectrum. And it's fairly mature. It's widely used today by existing satellites for inter-satellite communication, satellite to satellite. But satellite to ground, space to ground communication, this is a huge bottleneck. The market, though, is big and it's growing. It's about $2.1 billion today, and it's growing at about 32% a year. So lots of money in this market. If we look at the defense applications for it, there are some massive benefits to laser communications. They can't be detected, and it's very difficult to jam laser communications. So if you're trying to send a lot of data from a covert operating site, it can be done really easily, really well with laser communications. It's suitable for quantum key distribution. You can get these extremely high bandwidths, which is very useful. And with minimal infrastructure, you can have robust, secure communication in advanced operating bases, forward operating theaters, et cetera. With free space optical comms, there's also a clear pathway to these lightweight field deployable systems that offer a bunch of benefits to existing RF systems. So you're asking yourself, this sounds great. Why is laser comms not used everywhere? Well, there's a technical challenge to it, which translates into a cost problem. Anyone who's looked at a campfire in the blurry air above a campfire knows that the atmosphere has turbulence in it, and this degrades a laser beam. And the images in the bottom right, you can see what an uncorrected beam looks like. Fortunately, we have technology to fix this. It's been in use since the 80s and 90s in astronomy and in military use. It's called adaptive optics. And this measures the dispersion, the wavefront error of the light and can correct it into a nice tight beam, which then gets focused into a fiber optic cable.
Mark, sorry to interrupt. Your slides aren't moving with your...
Okay, what slide are you seeing, Moby?
The first one.
Okay.
Okay, but there are arrows at the bottom, so I'm able to independently navigate to the fourth one where he is. So if people move along with him, it works fine.
Okay, can everyone see I'm at why isn't laser comms everywhere?
Yep, we're there now.
Okay, great. Yeah, so adaptive optics the current systems we have are large, they're bulky, they require deformable mirrors, and they're really expensive, and they take a lot of fine tuning to make them work properly. And so we have large ground systems that are very expensive, and this is really holding back the massive proliferation of optical communication. Our breakthrough in our lab at U of T is that we took an adaptive optics system, which we use for astronomy research all the time, and we shrunk it from an optical bench, which is about a meter, this image on the left, onto an 8 millimeter large photonic chip. So all of the wavefront measuring, correction, et cetera, is done on this photonic chip. This is a huge breakthrough that's going to allow orders of magnitude savings in cost, in the size of the ground stations, and even in the data throughput that you can get out of them. When you can have a portable ground station, now you have things like ground station as a service that becomes possible, field deployable systems become possible. So it is an impressive and interesting breakthrough. Differentiating from other solutions, on the left, we have existing mature technology of RF. Everyone's seen the big satellite dishes that are around. Ultimately, they're bandwidth limited, and you have to deal with spectrum licensing. There are a lot of companies out today. Kai Labs is in the center here. They're a large French company making optical ground stations, but these are very big. They're very expensive, and it's fixed infrastructure. You can see it in the right side of that center image. That's a shipping container that all of the control electronics are housed in. So it's a lot of space to have a large system that does adaptive optics. There are companies doing small, lightweight, low-cost optical ground stations like Archangel Lightworks on the right, but they don't use adaptive optics systems. They can't fit that into the footprint and the size of what they're and the cost of what they're doing. So they're limited to around 10 gigabits per second. What we're doing is taking our adaptive optics system on a chip, a low-cost off-the-shelf optics from a commercial telescope supplier, and using our own proprietary optical design and control software to produce low-cost, robust optical ground stations. So why us? We have a great team. Professor Suresh Sivanandam is a tenured professor at U of T. He's the director of the Dunlap Institute for Astronomy and Astrophysics. We've got Dr. Robin Swanson, Dr. Ryan Dungy. They're experts in machine learning, control algorithms. Ryan is an expert in atmospheric modeling. And I come from a background of Canada's space industry, doing large space robotics programs. So we have a really good team. We have some depth in our bench. We have research agreements with the National Research Council for photonic chip design, and the Dunlap Institute. They have an engineering team that we can rely on for additional engineering support when needed. So we have the right people with the right experience and the right kind of bench to actually make this work. To talk a little bit about our company and our success so far, starting right in the middle, we incorporated in July of 2025. The work started back in 2023, and a bit earlier than that, we got about $450K in funding to the lab for development of this technology for the high throughput secure network program at the National Research Council. That let us get the chip designed in the first few iterations of it built. We've tested it in our lab. We've tested it with a simulated atmosphere. We've shown that it actually can measure the wavefront correction and wavefront error, and it can correct that error. So it is a viable product. The technology works. For the fall of this past year, we've been briefing Canada's major space and defense companies. So we've had meetings with senior leadership at Honeywell Space, at Canadensis, at MDA Space, and just down the street from us here, Kepler Communications. They all showed strong interest. They're all very excited for the technology. They asked us to keep up to date on how developments are going. In November of 25, we were accepted into the NATO Diana program. This is a really exciting program for us. It's a business accelerator within the NATO alliance, and gives us access to defense and business mentors, some non-dilutive funding, and access to the NATO ecosystem for rapid adoption services we can sell to governments and militaries very easily and quickly now because we're part of this ecosystem. We were shortlisted for the NRC's Quantum Internetworking Challenge. We expect to sign that contract in the next few weeks, and that will be another $450K of non-dilutive funding. That's split between the company Tightbeam and the lab at U of T. And we're about to go into foundry production for our 4th generation chip. This is the one that we'll be able to deploy and use in commercial systems that we're building. What are the next 18 months? We've got a good plan. We're at TRL 5 right now with our current development. We're building an integrated instrument in the lab that will be tested on Sky at NRC has a ground station that they use for satellite communication testing. We'll be installing our instrument there for some space to ground demos with satellite partners. Within 6 months, we hope to have that done and to have data ready to go on how our performance has worked and translate that into production optical ground stations that we'll be working with commercial partners for some pilot programs. We hope to have early revenue from some of those, and we will have a system that's ready for use and further development. Our ask is $4 million to help fund the next 18 months of execution. This will get us from where we are now at TRL 5 to somewhere beyond TRL 7 with initial revenue streams from pilot programs. And that is Tightbeam Photonics. Thank you very much. I'm happy to answer any questions.
That's fantastic, Mark. Thanks so much for presenting Tightbeam. Quick question for you from the chat. Can you talk a little bit about your IP?
Yeah, so there's a lot of trade secret and proprietary knowledge that we have from the decades of experience the team brings. The chip itself is protected by a patent, which is owned by U of T and NRC jointly. The two entities have reached an agreement on commercialization, and Tightbeam is the exclusive partner for that IP licensing. The agreement is not fully signed, but we're negotiating it right now. We have been, assured by both entities that we are the exclusive commercialization partner for the IP. As well, Suresh is one of the inventors of the patent, so we are deeply involved in this.
And last question, really quickly: why is no one in this space using laser communications today?
Yeah, that's a good question. So, I mean, the short answer is they are, but it's very limited. you have this issue of weather's a bit of an issue, and when you have really expensive ground stations, you can't afford to build multiple of them. You know, if it's 2 million or 5 million to build one ground station, that gives you one spot, and you don't get the geographical distribution that you need to make sure that you're always connected. If you can build a ground station for a few $100,000, which is what we enable, you know, you can do things like you can put ground stations, you can put a few dozen of them across the Canadian Arctic to make sure that there's always somewhere that you can reach from a given satellite. So I think once that cost comes down, which we can enable, you'll see this wider spread proliferation of ground stations.
That's fantastic. If you want to get in touch with Tightbeam Photonics, you can select the 11th slide. If you've been following along, there's a QR code which you can scan, reach out to the team for further discussions. You could also reach out to the UTEST team using our emails in the chat, and we can make warm introductions there as well. Mark, thanks again.